Okay, class, the last little lecture in this review series that we're going to do before Tuesday is VSEPR theory. A fun little theory, hopefully relatively straightforward to use, that can provide some good insight into some molecular geometry. And by extension, later on, we're going to see hybridization. Okay, valence shell electron pair repulsion theory. So, to be able to utilize this correctly, essentially you need to be able to draw a Lewis structure. And then once you've been able to do that, you can ascertain the shape using this little theory. And it's really easy. Basically, all it states is that the electrons around the center atom, which is being bonded, are repulsed by one another, and they want to be as far away from each other as possible. So these electrons can be in bonds, these electrons can be in lone pairs. There's a nuance to the theory that lone pair electrons are more repulsive than bonding electrons. There's some experimental data that shows that indeed this is the case. But it's a simple little theory to use, and it can give you the molecular shape quite nicely. One of the things to note that double bonds and triple bonds repulse the same as single bonds. So it doesn't matter if it's a double bond or a single bond, they've got basically the same repulsive power according to this theory. All right, some examples. MGBR2. So if we were to draw the correct Lewis structure of this, we would have a little pointer here. Here we go. The atom with which is the least electronegative and the highest bonding capacity in the center, that'd be magnesium. Magnesium had 2 valence electrons. Bromines have 7. So if you go through the process, you're going to come up with this Lewis structure for MGBR2. It's a nice and beautiful linear system here. And so in this case, we would call this, the little formula for the system is that the center atom's A and any bonding atoms are B. This is an AB2 system. And these electrons want to be as far away as possible from these electrons so they're on opposite sides. And that means that this entire molecule becomes linear. So these electrons are as far away from these ones as possible. This gives us a linear structure. If we move to the next column in the periodic table, we've got boron. So boron trifluoride here. This is a classic example. And in this case, this is a AB3 system. So the center atom bonded to 3 other atoms. There's no lone pairs, which would be the E in this. And if you go through and you draw your Lewis structure, you would have boron in the middle bonded to 3 fluorines. And actually both of these structures, this Lewis structure and this Lewis structure, share something in common, that being that the center atom has an incomplete octet. And these are some of the exceptions to the octet rule. Now, back to the task at hand, which is valence shell electron repulsion theory. So these electrons in this fluorine bond want to be as far away from these ones as possible and as far away from these ones as possible. And to do that, they're all essentially 120 degrees apart. So they're all on the same on the same plane, but they're 120 degrees apart from each other. And because there's 3 atoms here, we call this structure trigonal planar because it looks like a triangle and it's on a plane. Okay, excellent. So just as a really simple sort of table here, AB systems, AB3, AB4, AB5, AB6. The good news for the class is that we're dealing with carbon, we're dealing with oxygen, we're dealing with nitrogen, all second row atoms, AB5, AB6, we're talking here expanded octets. So these ones are not particularly common in organic chemistry. What we're dealing with is up at the top. So the electronic configuration around that atom can be tetrahedral. And because there's no electron lone pairs here, that means that the molecular configuration is tetrahedral. So AB2 systems, these are linear. AB3 systems are trigonal planar. AB4 systems, which would be carbon tetrachloride or methane, CH4, tetrahedral. AB5 and AB6 would be trigonal bipyramidal and octahedral themselves. I don't know if we don't really need to do any examples of these for what we're dealing with. We're almost exclusively looking in these areas here. Now, when you have lone pairs, then the things start to change slightly. So we'll use water as our best example here. So the Lewis structure of water, no surprise, it's this. If you look at the center atom, it's bonded to two atoms, H and H, and it's got two lone pairs. So this system is an AB2E2 system, and the center atom has 4 sets of electrons. Two sets are bonded to the hydrogens, and 2 sets are lone pairs. So the actual electronic configuration of this molecule is tetrahedral. So these, and a true tetrahedron is 109 degrees. So you would think that this would be 109 degrees, this would be 109 degrees, all these bond angles would be 109.5 degrees. But lone pairs actually have more repulsive power, so this little angle here gets squeezed, so it's slightly less than 109 degrees. But overall, if we're talking about the electronic structure, these 4 sets would make a tetrahedron. If you're looking at the molecular structure, though, we don't worry about the lone pairs for that. We're only looking at the atoms. So this going here to here, this would be a bent molecule. Fun. So water's bent. This is why I like to draw water like this, because it looks bent as opposed to being linear. Okay. So there are a couple, like we could do a big long list of systems. Like I've done an AB2E system, an AB3E system, an AB2E2 system. Just to show you some of the possibilities when we've got lone pairs. So in this case, if we're looking at this system here for the electronic configuration, these electrons want to be as far away as those. These want to be as far away as those and those. So this again is going to be a trigonal planar electronic configuration. But if we're looking at the atoms for the molecular structure here, this would be a bent molecule. If you've got a center atom which has got 3 bonds in a lone pair, like nitrogen, for example, again, the electronic configuration is tetrahedral, but if you're only looking at the atoms, we've got this sort of structure here, which would be a trigonal pyramidal system for the molecular shape. Tetrahedral with 2 lone pairs. Again, this would be water, perfect example. So the electronic structure is tetrahedral, but the molecular shape, if you're only looking at the atoms, is bent. Now, carbon itself it can have a maximum of 4 bonds. So the shape is pretty limited. It can be linear, it can be trigonal planar, or tetrahedral. And I thought of an example where it was trigonal pyramidal here. We'll do that right next. So methane. Molecular shape is tetrahedral. Electronic configuration is tetrahedral. I lost my pointer. our friend, the carbanion, which we talked about when we're doing formal charge. So the electronic configuration would be tetrahedral, but if you look at the atoms, this is like it's a trigonal pyramidal structure. Our friend, the carbocation, when we were looking at the formal charge. So these three sets of electrons want to be as far apart from each other as possible. So this makes this a planar system. They're all 120 degrees. And it's a triangle, so trigonal planar for carbocation. If we're looking at ethylene, so, and we in this case, we've introduced some double bonds into the system. And remember, double bonds don't repulse any more than single bonds. So this would be 120 degrees, this would be 120 degrees, this would be 120 degrees, and this carbon would be trigonal planar, as with this. In acetylene, triple bond, single bond, these would try to be as far away from here as possible. So this would be a linear system, just like this would be a linear system. So we've got a linear molecule here. Okay, now let's go back and look at those two molecules we did for our Lewis structures and see what they would look like. So let's share a different screen here. So what molecules were we looking at here? We had carbon dioxide. So in this case, these sets of electrons want to be as far apart from each other as possible. So we would have this is effectively an AB2 system, center atom, two bonding atoms. So this would be linear. Okay. So here, now I've actually drawn this in a way which isn't quite, it's not going to be, so we would want these lone pairs here to be as far away as possible from those and as far away from possible as those, right? So I've actually drawn this in a way which isn't particularly good. So this system, center atom is A. We've got, it's AB2. We've got a lone pair here, AB2E. So really, we should have our electrons out like this. And the actual, this would be approximately 120 or slightly less, or slightly more, 120 degrees. So electronically, this would be trigonal planar. But if we're talking about the molecular geometry, here we've got oxygen, sulfur, oxygen. This should be bent from as a molecule, molecular shape. So carbon dioxide, linear molecule. Sulfur dioxide is a bent molecule. Okay, let's go back to the other screen here. Let me share. Let's go back to VSEPR Theory. Okay, so the last little part I wanted to talk about was in Gen Chem, we related the molecular shapes to what we would call hybridization, and we're going to do hybridization next week. But by and large, this works really, really well. We'll see that there's a couple of examples where it doesn't when we're talking about resonance, but for AB systems, which has got a linear shape, the hybridization is going to be sp2. In AB systems, where it's trigonal planar, the hybridization is going to be sp2. And when we've got AB4 systems, this will be tetrahedral, and we have got, it's going to be sp3. So one of the things to remember is that in a linear system, you've got those two bonds which want to be as far away from each other as possible. If you count S is 1 and P is 2, this equals 2, right? So you want two bonds far away. In a trigonal planar system, you've got three bonds which want to be far away from each other as possible. S1, 1 plus 2 equals 3. In a tetrahedral system, you've got four bonds, right? 1 plus 3 equals 4. So it's an easy way for, at least that's how I remembered it. Okay, but we're going to do hybridization next week. Okay, and that basically ends this little lecture on VSEPR theory.